In this video for section 10.3, we're going to look at situations where our samples are paired. This means that the values in one sample are matched with the values in the second sample, so they will no longer be independent. So an example to think about this is if we have a paint manufacturer and they want to compare two paint mixes and the amount of space or the number of square feet that 1 gallon of paint will cover. They could give 1 gallon of paint to one painter, another gallon to another painter, have them both paint, use up the entire gallon, and then calculate how much area is covered. This would be a situation where we have independent samples because the amount that one person can cover with their paint doesn't affect the amount that the second person can cover with their paint. The problem with this design, though, is that different people paint differently. So one painter might be putting on a thicker coat than the other, and this could result in less area covered. It doesn't have anything to do with the paint itself, it's the painter's technique that's causing the difference. So it would be better if we had the same person painting with both paints, and that would eliminate the effect of painter's technique on our results, or it would control for the painter's technique. So paired data sometimes occur as before and after measurements, or we have the same group of people repeat a process with different products. But either way, we have one person doing basically two tests or testing two products. So looking at example 10.7, this is going back to the section 10.2 when we looked at the test with the ink cartridges. This time, they're going to do the test using paired samples instead of independent samples. And they would do this because they might think that different users may be using different amounts of ink. So some people might print a lot of pictures, which is going to use up more ink than people who print mostly text. So what they're going to do this time is take a sample of 6 users and have each user use the name brand cartridge and the generic cartridge. And the results are in the table below. This is how many pages each person was able to print with each type of cartridge. We're going to conduct the test using alpha equals 0.05. So first I'm going to write my hypotheses. When we're using paired data, a lot of times you'll see the hypothesis written in terms of mu sub d, and the d here stands for difference. So our difference that we're going to calculate is going to be the mean of the name brand minus the mean of the generic. So in the last section, we usually wrote these out. It would be like mu1 minus mu2. This time we're going to use mu sub d to stand for that subtraction. So for my alternative hypothesis is that this difference is going to be greater than 0 because I'm thinking that the name brand might print more cartridges or print more pages than the generic brand cartridge, and so that would make this difference a positive number because the name brand is going to be bigger. So my alternative hypothesis is that mu d is greater than 0, and that means that my null hypothesis is going to be the opposite of that, so it would be that mu d is less than or equal to 0. So those are my hypotheses. Now we're going to go to Minitab. I have the data already entered here from the table on the page. So these are the values. I labeled the columns name, brand, and generic. And then I'm going to go up at the top to stat, basic statistics, and I'm going to go to paired T, which is below to sample T. Now this time, I have each sample is in a column because I have the data entered into Minitab in columns. If the problem were giving me mean and standard deviations, I would enter summarized data. So I would select that, but that's not what I have. I have each sample in a column. So I'm going to click in the box and then select sample 1 to be the name brand and sample 2 to be the generic. Then I'm going to click on options. I can see here I'm looking for the mean of sample 1 minus sample 2, so make sure that you're keeping those which one is which correct in your previous screen. And then hypothesized difference is going to be 0 because my hypothesis is that mu d is greater than 0. I'm going to change the alternative hypothesis box to difference is greater than hypothesized difference to match my alternative hypothesis. Click OK, and click OK again. So here are my results. It's telling me the mean and standard deviation of each set, which I didn't ask for, but that's helpful to see sometimes. And then if I go down to the test, I see my t-value and my p-value. So again, a lot of times in the homework, you're going to be asked to enter the t-value. My p-value here is what I'm going to use to answer the question. If I want to see more digits, click on that, and I can change the number of decimal places. So 0.0795 is my p-value. So what do we do with that? We compare it to alpha. Is the p-value less than alpha? No, it is not. 0.0795 is not less than alpha. So p-value is not less than alpha. That means that we cannot reject the null hypothesis. Or we fail to reject the null hypothesis. And since we're not rejecting the null hypothesis, what does that tell us about our situation? Well, that tells us that we cannot say that the name brand cartridges print more pages than the generic cartridges. So we do not have evidence that the name brand prints more pages, or we do not have evidence to support our claim.